Now, before I was Gresham Professor of Geometry, in fact, before I was a professional mathematician, I was, in fact, a mountaineering leader for the wonderful organisation West of Ireland Camps. And I had to do a lot of navigation in my job then, and so it is with great pleasure that I decided to present a lecture today about navigation and how maths can help us in that very important job of telling us where we are. Okay, so I'll start off with a poem. So doing the research for this lecture, I was delighted to come across the Ballad of Gresham College, which was indeed written about this very organisation in 1660, which was not very long after the college was founded. It's a poem which talks about, or a song, which the great achievements of all the Gresham professors in their many different areas of work. I thoroughly recommend that you read it. And here we are. The college will the whole world measure, which most impossible conclude, and navigation make a pleasure by finding out the longitude. Every tarpaulin shall then with ease sail any ship to the antipodes. Okay, and we will find out a little bit more what this is about as we go through the lecture. But do have a look at this. This is verse 26. It's a long song. Okay. Great achievements by Gresham professors. Okay, so knowing where you are is very, very important part of human civilization. So the earliest humans that went out for a hunt would need to know where the animals were and need to know how they could get back to their campsite. So very, very important part of human existence. Still incredibly important now to know where you are. How many of you have a sat-nav device, for example? In fact, probably all of you do if you have a mobile phone. So early navigation would be a matter of where you go over the hill, turn left, and then right at the first big tree. Okay, that's sort of navigation by dead reckoning. And that's okay for short distances, but when you need to go further, you need to do something more complicated, and much of traditional navigation until quite recently was done by observing the stars. So we'll have a look at those techniques in this lecture. Nowadays, we use electronic means. In particular, we use GPS. So, as I say, my phone here has GPS. It's very good. It will locate me to within a few yards. It's really very, very accurate. None of these advances in navigation would have been possible without mathematics. They are all very reliant on mathematics, even dead reckoning, where you have to walk a certain distance. You have to count the number of paces that you make. That requires mathematics. So mathematics has stimulated navigation, but I shall also show you how the challenges of navigation have in turn led to advances in mathematics. This, for me, is the wonderful virtuous circle of mathematics. Mathematics stimulates innovation. Innovation stimulates mathematics. And we see this in many other fields. And as Professor of Geometry, of course, I'm very pleased to say that geometry itself was stimulated greatly by navigation. So if you want to work out where you are, the first thing to do is to have some sort of indication of what's around you. And of course, what that means is you need to draw a map. And here are two early maps. Well, this one is particularly early, but remarkably good. This was the Ptolemaic map, which was printed or drawn about 2,000 years ago, and used mathematical principles, which relied on Euclidean geometry, and is actually pretty good. You can see England there, Spain, India, not quite right, but basically it looks pretty good. A remarkable achievement for 2,000 years. Here on the right is the Mappa Mundi. If you ever go to Hereford Cathedral, do go and have a look at the Mappa Mundi. I really like the Mappa Mundi. It isn't a great map. Okay? In those days, the purpose of a map wasn't necessarily to show you where you were geographically, but was certainly to show you where you were theologically. And the Mappa Mundi aimed to do that. It has Jerusalem at the center, and you have various aspects of the Christian faith displayed. So that's the Mappa Mundi. Do please go and have a look. However, when I think of a map, I don't think of a Mappa Mundi. I don't think of the Ptolemy map. I think of one of these. Okay, this is what I kind of grew up on, the wonderful Ordnance Survey map. This is the 50,000 map, which came out round about 1974. It's replaced the 1 inch to 1 mile map at that point. And Ordnance Survey maps have been really the hallmark in high-quality map making. And the Ordnance Survey itself, I'm pleased to say, employs a large number of mathematicians to do that. It was founded in 1747, and the reason it was founded was that at the time, the Scots were being somewhat awkward. They just had the Battle of Culloden. They needed to sort out what was going in Scotland, and they realised that to do that, you needed good maps. Okay, so I'm sorry if there's any Scots in the audience. I apologise for this terrible imperialistic thing. But it was founded by David Watson, Lieutenant Colonel, and the Ordnance Survey was very much part of the military and essentially still is very linked in with the military. These are the 25,000 scale maps, which came out again about the same time as the 50,000 map, which are the ones that I typically use for my own navigation when I'm on the hills. The technique that the Ordnance Survey used to construct the maps was based centrally on Euclidean geometry and trigonometry, basically triangles. So what they did was have a series of points, triangulation points. You'd start with two of them, A and B, and you'd extremely carefully measure the distance from A to B. That might well be by extending a set of rods, which were carefully controlled so that they knew the length, even though temperature compensated, so they could extremely accurately measure one length. And then from that, you'd measure a series of triangles to the other points using a theodolite, which you could measure angles with down to about a quarter of a minute of arc, and build up this series of triangles. And then when you got to sort of some distance along, you'd then go and measure this distance here and compare that against the distance predicted by your triangulation, and providing they were within a series, close enough to each other, you could then carry on with the entire triangulation. So maps were constructed by a set of triangles, and then you build out from those triangles to a large region. So extremely closely based on Euclidean geometry. What are these points here? Well, in 1936, a set of trig points was built around the country. Again, if you're a navigator like me, when you're on a mountain, finding a trig point is great, then you know exactly where you are. And the first trig point was built in Northamptonshire, at a place called Cold Ashby, in 1936. And here you see some of the original surveyors using these trig points to line up with the next one they could see. Here's a more recent navigator. There we are. That's me. This is Monty the dog and Benji the dog. And I'm carrying my map here. And I will give a gold star to anyone that can tell me where I am. Okay. It's not completely obvious. I know where I am, but I'd be interested if you can work out where I am. And lest you think that that's what navigators look like nowadays, this is the modern equivalent of the Ordnance Survey surveyors. And modern surveying is now done with GPS. And as well as using triangulation, extensive use is made of aerial photographs and satellite photographs as well. So it's quite a sophisticated process making an Ordnance Survey map. And again, if you just look at one of these and see how much detail there is in each kilometre square, you realise how much work has gone into making one of these maps. And these have saved my life on many occasions. I quite literally mean that. And so here's an example of a 25 scale, 1000 scale map. This is Bath, where I live, and that cross there is my office, if anyone wants to visit me at the University of Bath. So let's think a bit more about how one might use a map. There are two ways of looking at a plane, which a map is basically a representation onto a plane of paper of something which is a three-dimensional surface. One is to think of this as a point in two-dimensional space where you have x, y coordinates. So you can represent any point in two-dimensional space by two coordinates x and y, and that allows you to precisely specify where it is. This is a Cartesian coordinate representation of location. And the Ordnance Survey basically uses this to identify points precisely. You have what we call a grid reference, and each map you have these big squares which divide up the UK. Bath sits on square ST, and then each map is then divided into grids. If you can see here, there are grid lines, and then to exactly locate something like my office, you find the coordinates of that, and then you walk along a bit there, and you walk up a bit there, and you build up this grid reference here, and that precisely locates you where you are. So if I want to know exactly where I am on a map, I will make use of Cartesian coordinates. And when I teach my students about coordinates, I generally use a map as a good example of why coordinates are useful. However, for the purpose of actually walking around on a map, Cartesian coordinates are not particularly useful, and what is much more useful are polar coordinates. So I've indicated polar coordinates here. A polar coordinate representation of the same point gives you an angle theta and a distance r. And if I want to walk at a particular angle in a particular direction, I will make use of my trusty compass. And here is the compass that I use. And believe it or not, this compass is 45 years old and has never let me down yet. Okay. I did try to replace it, and I came to the rather worrying conclusion that a modern compass is less accurate than this, because the oil in the more modern compass was more viscous and delayed the motion of the needle, so it didn't respond quite as quickly to my moving around. So that was an interesting discovery. But the way I navigate typically is I would set my compass to an angle. If I want to go from here to here, I set that to an angle. You can easily navigate to an accuracy of about 1 degree if you're using a reasonable compass. And then you walk a distance r in that to get you there. And to calibrate, I've walked over a lot of mountains, and I find that I walk 660 double paces per kilometre. So when I walk with my wife, I'm an extremely boring companion, because all I'm ever doing is calculating how many steps that I've walked and then doing the calculations. So she says, "Why are you so silent?" And I said, "Well, contemplating the hills." Actually, I'm counting the number of steps I'm doing. But that's how a mathematician navigates, and if you do it that way, essentially you can't get lost because you're so boring. You're just counting, changing, counting, changing. And that's how I get around on the mountains. So to know where I am on the map, Cartesian coordinates, that's one way of doing geometry. If I want to walk around, polar coordinates, another type of geometry, but it's maths all the way. So that's the Ordnance Survey. One of the great successes of the triangulation approach was in the 19th century when, of course, Britain had the empire and India was part of the empire, and a decision was made to survey the whole of India, and this was done by triangulation. And the thing called the Great Trigonometrical Survey of India was made, where a set of triangles was built up from the bottom all the way to the top, and you can see the triangles as they're forming. And this was done incredibly carefully, and a very, very accurate survey was made. And although he didn't start the survey, the person that did much of the work for it was none other than George Everest. And of course, one of the things he surveyed were the mountains, and therefore the highest mountain that he surveyed was named after him. And that's why Everest is named Everest. Of course, it wasn't called that originally, but that's what we called it. And it's not such a bad name. So it's up there. So that's the Great Trigonometrical Survey. So let's show you now a little bit why navigation stimulates mathematics. The original mapping and much of the mapping of the UK is done using triangles with straight sides. But when you're doing something as big as India, you're going over a large amount of the Earth's surface, and the Earth, as hopefully we all know, although some of my correspondents disagree with me, is a sphere. Okay, so the Earth is a sphere, and when you draw triangles on a sphere, and those triangles are large, the curvature of the Earth becomes very important, and you need to develop mathematical techniques to deal with that. And this brings us into the wonderful field of spherical trigonometry. So what I thought I'd do quickly is give you a quick primer in spherical trigonometry, and then we're going to come back to that later on when we look at celestial navigation. And I do this without any apologies. I'm Professor of Geometry. I'm allowed to do some geometry. Okay. So a spherical triangle is a triangle drawn on the surface of a sphere. And in a spherical triangle, you have the sides, A, B, and C, and you have the angles, big A, big B, and big C. And we tend to think of these sides in terms of the angle that they make relative to the center of the sphere. So these triangles behave a little bit differently from the triangles on the plane, and working out how they behaved, it stimulated an area of mathematics, which then became very important later on. These are the fundamental equations of a spherical triangle. These equations here allow you to calculate, for example, that length there in terms of the other sides. So if I want to work out that length, I know that angle and those two sides there. I can use these, and these are called the extended or spherical cosine rules. If you're used to the cosine rule in plane trigonometry, these are extensions of those. And this is called the spherical sine rule. And these two allow you to what we call solve a triangle. So if I know that angle and those two sides, I can work out that side and those two angles. And we'll see how that's important later on in celestial navigation. But one of the nicest things about spherical triangles is if you draw a triangle on a map like this, and you measure the angles. Can I have some slides back, please? There we go. If you measure the angles on a plane map and add them up, you get to 180 degrees, or as mathematicians say, pi, radians. If you do the same on a spherical triangle, you don't. You get something which is pi plus 3 times the area of the triangle. So the angles in a spherical triangle do not add up to pi or 180 degrees. And the bigger the triangle is, the less that occurs. Okay, so you can get triangles adding up to far more than 180 degrees. Just an aside, so spherical triangles are really, really important for the sphere and very important for navigation, but they are just one example of a geometry which is different from the geometry that Euclid came up with. I'm not sure what's going on here. Again, I can see it on my thing. There we go. I'm not doing anything. At the same sort of time as all this was going on, a whole area of non-Euclidean geometry was being developed in the 19th century. And then non-Euclidean geometry, which is the geometry of triangles and stuff not on the plane, led to directly to general relativity and many other advances in the 20th century. So navigation leads to non-Euclidean geometry, leads to relativity. And we'll see presently how relativity comes back into navigation when we get onto GPS. So I've started talking about the sphere, and when you're talking about the sphere, we obviously want to be able to do maps of the whole of the Earth. If I want to go from England to China, then I need a map which shows me the whole of the Earth. So how do we map the world? Well, the map's a sphere, and the world's a sphere, and it's not very convenient to carry a globe around us. We basically want something which is on a piece of paper. So we need to find a way of representing the Earth's surface on a plain piece of paper. Now, it's useful to have coordinates which help us do that, and the most important set of coordinates are latitude and longitude. So latitude and longitude, a point on the Earth's surface at position x, y, z, you need 3 points because we're in 3 dimensions, has a latitude, which is theta, and a longitude phi, and every point on the Earth's surface can be measured in terms of these. So latitude is the angle up from the equator, and longitude, for reasons which will become obvious presently, is angle measured around the Earth from Greenwich. And Gresham College is pretty close to Greenwich, so it's more or less measured relative to Gresham College, which is kind of nice. So that's longitude and latitude. So how do we put the sphere onto a plane? Well, we have a problem. And the problem is a mathematical problem. It's called the hairy ball theorem. Most mathematical theorems are boring. They're called Pythagoras' theorem or something like that. But the hairy ball theorem is a great theorem. And basically says if you're trying to represent the sphere on a plane, then you've got a problem, because somewhere you're going to distort things somewhere else. Okay, you can't do it in a non-distorting way. It says a lot more than that, and I paraphrase a great deal, but that's one of the consequences of the hairy ball theorem. And this hits you a lot. It hits me a lot in weather forecasting, which is one of my areas of work. And what it means is that it doesn't matter how you draw a map from the sphere onto a plane, somewhere you're going to have to make a compromise with accuracy, and all maps are a compromise between accuracy, usability, and politics. Okay, so let's see how this arises. Here is the most famous projection of the sphere onto the plane. This is the Mercator projection, which goes right back to 1569. I'm sure many of you will be very, very familiar with the Mercator projection. Lines of latitude and longitude are straight, which is really nice. Another very important thing about this is that if you go at a constant compass bearing, so for example, if I wanted to steer northwest, then that would be a straight line on this map. So that's the Mercator projection. Geometrically, how's this done? The way the Mercator projection works is that you have the sphere and you draw a cylinder all the way around it like this, and you draw a line from the center of the sphere through to the point on the Earth's surface out to the outside of the cylinder. So you then, on that point in the cylinder, you unwrap the cylinder and you get the Mercator projection. Now, the transformation in terms of this, if that's to the distance up here, which we call the Mercator scale, and that's degrees latitude, is that the distance up here is the equal to the kind of radius of the Earth times the tangent of the angle. So that's the mathematical equation. This is pretty good, close to the equator. It's a fairly kind of linear relationship between latitude and Mercator scale. But as we approached 90 degrees at the poles, so tan theta becomes infinite, and this becomes very, very distorted. So the Mercator projection has advantages and disadvantages. The key advantage, it's very simple. You've got lines of latitude and longitude are straight, and from a point of view of a sailor on a ship, the rhumb lines, which are the lines of constant bearing, are straight. The disadvantage is you get this huge distortion at the poles. So if you look at Greenland here, Greenland ends up being larger than Africa in a Mercator projection. And that's not great. I mean, from the point of view of Britain, this was fantastic because it means that Britain looks really big because we're northern, and America looks really big because that's northern, and these sort of other places don't look so big because they're nearer the equator. But from a political point of view and from a kind of representation point of view of the Earth, the Mercator projection has a lot of problems. It's been replaced by other projections. So one that you often find in schools is a thing called the Gould-Peters projection, which was introduced in 1973. And in the Gould-Peters projection, you still have a cylinder with the Earth, but instead of the Earth being inside the cylinder goes through the middle of the Earth like this. And what this means is that you get much less distortion at the poles, and the equatorial regions are essentially larger. So the nice thing about this from a kind of political point of view is that it makes Britain look smaller and Africa look bigger. Okay, I'm a little bit cynical about this because it essentially takes one distortion and replaces it by another distortion. So that's the Gould-Peters projection. As I say, the hairy ball theorem means it doesn't matter what you do, you're going to have distortion somewhere. The Times and National Geographic make use of a thing called the Winkel-Triple-Bartholomew projection, which is an excellent compromise between all these things. It basically gets areas correct, introduces relatively minor distortion. It does this by using cones rather than cylinders. And so if you get the Times Atlas of the World, that uses the Bartholomew projection. The disadvantages of the Bartholomew projection are firstly that lines of latitude and longitude are no longer straight, so it's harder to use. And run lines, the things that navigators need, are definitely not straight. So the point of view of actual navigation around the Earth, this isn't very useful. In terms of political representation of what the Earth is like, it's pretty good. You can see Greenland now looks much better scaled. But as I say, all these compromises are forced on us by the mathematics of the underlying geometry. There's not much we can do about it. I just want to tell you a little bit about some of my own work. One of my jobs, well, one of my biggest jobs, is I work with the Met Office to do weather forecasting. The Met Office has to forecast the weather on the whole of the globe, and that's done using computer methods. And what you do is you divide the globe up into small regions. You, what we call discretize the equations for the weather on the small regions. So you solve over a small region, and then you kind of glue it all together to get the weather everywhere. Until recently, the Met Office have been using latitude and longitude coordinates, which introduces distortion at the poles. They are trying to move away from that, and we experimented with various different types of ways of doing this, and have come to the conclusion that the best way to do it is actually to divide the entirety of the world into very small triangles, which are arranged in what we call an icosahedral pattern. And these are the sort of meshes that we use to calculate the weather on, and this is where we've concentrated the points into a particular region so that we can resolve a storm over there. So just to say that map projections, as well as producing maps, are also used for other things like forecasting the weather. Okay, well, hopefully things are settled down now, so we'll have less fireworks. And I want to talk now about celestial navigation. So when we think of navigation, we often think in terms of navigation by the stars. We've just, I think it's just about coming up to Epiphany, or it's Epiphany around about now, where the three wise men came from the east following a star. Okay, so they were clearly navigating with a star. And finding your location on the Earth is a hugely, hugely important problem. If you've got a ship full of very, very valuable cargo or full of people, what you do not want to do is get lost so that you run into the rocks and the ship gets destroyed. Or simply you want to get to where you need to get to as quickly as possible. So navigating your way around the Earth on the oceans where you're well outside of any land is a very, very important piece of well, it's very, very important for the economic development and safety of the world. So, as I said, the natural set of coordinates that we need to navigate with or represent points on the Earth are latitude and longitude coordinates. So to navigate on the Earth, we need to find our latitude and our longitude. So Columbus was a great sailor. He sailed from Spain over to the Americas. He had a very rough idea of how big the Earth was. In fact, he thought it was much smaller than it actually was, even though the Greeks knew how big it was. And he navigated mostly by dead reckoning. So he would get some estimate of how fast the ship was going by dropping essentially ropes out the back of the ship and timing that. And he used a certain amount of crude celestial navigation. He still got to America, but he thought he was in India rather than America, which was problematic. Nowadays, we, until sort of quite recently, navigators on board ships did it by really watching the stars and making very, very careful measurements of it. So, as I said, to navigate, you need to know your latitude and your longitude. And these are two different problems. Calculating latitude is quite a straightforward exercise in geometry. And the way you do it is you measure the height of a celestial body, conveniently the sun, above the horizon, and a convenient time to do that is at noon when the sun is at its highest point. So what you do is you kind of constantly measure the sun, and when it gets to the highest point, you record that angle using a sextant or some other measuring device. And a modern, or even devices used in the 18th century, could easily measure that angle to about half of a minute of arc. At the same time as measuring it, you get clever mathematicians to work out the angle of that body relative to the equator. This is called the declination. So the declination is the angle the sun makes relative to the equator, and this varies during the year. So winter, where we are, it's minus 23.45, so it's below the equator, and that's due to the tilt of the Earth. And at midsummer, it's 23.45 degrees above the equator, so it goes up and down. And again, that's due to the tilt of the Earth as it moves around the Earth's orbit. And this is a formula which allows you to calculate the declination precisely. N here is the number of days from the 1st of January. And this formula accounts for the ellipticity of the Earth's orbit. So basically, you'd have people called computers who would calculate this formula and tabulate the values of the declination for every day of the year in tables called ephemerides. Okay. So that's the declination. How do you make use of that? Well, here's a nice bit of geometry again. Here's the Earth tilted over. That's the sun. That's the declination. Let's suppose that the latitude is phi. Then a fairly simple piece of geometry shows us that the angle z that the sun makes to the horizon in degrees is 90 plus the declination minus the latitude, or if I turn that around the other way, the latitude is 90 plus the declination minus the altitude of the sun. So you measure the altitude of the sun at noon, you look up D in the tables, and that gives you your latitude exactly. So latitude, pretty easy to find out. Longitude, much harder. And much, much harder. That poem I read at the beginning is all about the Gresham geometers trying to solve this impossible problem, and calculating longitude took on the reputation of being like turning lead into gold or finding the Holy Grail. It's a sort of problem you joked about because it was thought to be impossible. However, very important. It was tackled by Newton, several astronomers royal, and here we have Hooke, who was my predecessor as professor of geometry, who worked on the same problem. And this is his portrait hanging in Gresham College. And finding longitude was so important that the British government in 1714 offered a prize of £20,000 So it's several million today for anyone that could solve it. So how do you find longitude? Well, basically the key to finding longitude, and in fact the key to almost all of navigation nowadays, is finding time. If you can find time, you can find longitude. The Earth rotates 360 degrees in 24 hours. That means in 1 hour, it rotates 15 degrees. So every hour you measure, the Earth is rotated 15 degrees. And that means every 4 seconds, you travel 1 minute of longitude. That's 1/60th of a degree of longitude. 1 minute of longitude is equal to 1 nautical mile, which is slightly more than a mile. And therefore, if you have a clock that can measure time to an accuracy of 4 seconds or better, then you can locate your position to 1 mile or better. Okay. And that's quite a kind of ask of a clock to get an accuracy of 4 seconds, given that the clocks on a ship have to travel all around the world in all sorts of different temperatures, all sorts of different humidities, and have to deal with the rocking of the ship at the same time. So there was a huge controversy in the 18th century about if you're going to measure time, should it be done using a celestial clock or a mechanical clock? And the first solution to this problem came from Galileo. So if you were at my lecture, not on climate change, but the one before that on chaos, I talked quite a bit about Galileo. I'm a great fan of Galileo, and he and I have the same birthday, which I'm very proud of. So anyway, there's Galileo. And Galileo had a look at the sky with one of the first telescopes, was the first person to realize that Jupiter had moons, and he saw that the moons went around Jupiter very, very precisely. You could exactly predict when a moon would eclipse Jupiter. So that gives you a celestial clock. It means that if you look from where you are at the moons of Jupiter and see what their configuration is, you know what the time is in an absolute way. It's a kind of celestial timepiece. And by doing that, you can find your longitude. Now, the problem with this is on board a ship, spotting Jupiter and seeing where the moons are is basically impossible. It's too delicate. But on land, this could be done very precisely. So calculating longitude using the moons of Jupiter became a standard technique for making maps. And there's a nice sort of story behind this. In Louis XIV's time, he decided France would be the great scientific nation, and they would get really accurate maps of France. So he commissioned his astronomers to look at Io, which was one of the Jupiter's moons, and by looking at the eclipses of that to calculate longitude. And so they did that. They produced the most accurate map ever produced at the time. And one of the consequences of producing the accurate map was they found that France was actually smaller than they'd originally thought. And this concerned Louis XIV, who said he was losing more of his realm to astronomers than to his enemies. Okay. So our scientists get into trouble. So that was the celestial clock. Very, very good method on land, hopeless at sea. The next idea was to use another timepiece in the sky, which is the moon. And in the 1750s, a guy called Tobias Mayer, who's a map maker in Germany, came up with the idea, produced a practical method of, by plotting the moon in the sky and seeing its distance relative to various stars and knowing exactly where the moon would be from other calculations, which are highly geometrical, you could see what the celestial time was, and then from that work out your longitude. And that's using a celestial clock. It was very popular with the Astronomer Royal, Maskelyne at the time, because, it was a nice, precise geometrical method using the heavens. You knew what you were doing. Just to show you the link between that and mathematics, Euler, who was a wonderful, possibly one of the greatest mathematicians ever lived, a Swiss mathematician, came up with a set of equations, these are called differential equations, which describe the moon's motion, and he was able to solve those differential equations, and by solving those differential equations, he could show where the moon would be at any one time, and that was what Mayer used to then produce his lunar tables, which could be then used for navigation. And I'm pleased to say that Leonard Euler's work was recognised by the Longitude board, who gave him £800, 3,000 to measurement. You have to multiply these by significant. There's a reasonable amount of dough that he got for doing some good mathematics. Lunar method works, but the problem with the lunar method is you have to make very, very, very precise measurements, which are still very hard, and then the calculations took a very long time. By the time you'd done the calculations, your ship was probably a long way away from where it was when you wanted to actually know where it was. So that was the problem with the lunar method. And the real solution came not from a mathematician, but from a clockmaker. This is a very famous story, John Harrison, who, instead of trying to measure where things were in the sky, looked at how to improve the design of clocks. He came up with various designs of clocks which were essentially frictionless and were compensated so that they would account for the various changes in the ship and so on. He built his first clock, which was compensated, called H1, in 1736. You can see this at the Greenwich Observatory. It took him about 25 years to then perfect the design down to a watch, which is called H4. This is I think of as the supercomputer of the time. This was, this watch was accurate to much better than the 4 seconds per day that you need to get the nautical mile right. Incredible piece of engineering. And here he is. He's holding a watch here, which isn't this one. At the time they did this picture, this watch was being inspected by the Astronomers Royal to make sure that it was okay. And so he's actually holding an earlier watch there. But essentially the breakthrough came in navigation by this ability to combine mechanical perfection with great mathematics as well. I really like this. My own work, my own research is all on how you use computers to solve real-life problems, and that requires good mathematical knowledge, I hope, combined with machinery. And it's that combination which essentially is how the modern world now works. So that was the beginnings of the modern world. This is the start of the technological revolution. Just very quickly, for those of you who like these sort of things and maybe navigators yourselves, this is how modern navigation works. The way modern navigation works, if you're using celestial navigation, is you estimate where you are. You have what we call an assumed position, which is largely obtained by dead reckoning. You measure the height of a celestial object at a precise time, so you use your watch or chronometer to tell you exactly what the time is. You measure the height of that object. At the same time, you look up in your tables where that object is, what's called its geographical position is, which is the point on the Earth's surface directly underneath that object. So you have your assumed position, your geographical position. Then if your assumed position is here, that's the North Pole, and that's the geographical position. You solve this spherical triangle, just like the spherical triangle we had earlier, to calculate the azimuth, that is the angle between the North Pole, the line to the North Pole and that object, and also this angle here, and also this angle here, which allows you to work out the declination of that object, the height of that object that you'd see it, using these wonderful formulae here. And nowadays we do this on a computer, but in earlier times this was done by tables. And that allows you to calculate the height that you would see the object at from this position, and you then compare that with the actual height that you measure, and the difference between them tells you how far away you are from this position in the direction of the azimuth to the geometrical position. So this is all a bit quick, and I've gone through rather fast, and you can read about it in the transcript. But this is how the modern intercept method works, and it's a very robust method for finding your position at sea using a sextant and tables. Okay, so now I'm going to move on. We've had a look at how you navigate relative to the stars, but modern navigation has essentially moved beyond this. And the big stimulus for this came from, as ever, war, and in particular the Second World War. And in the Second World War, there was a vital need to navigate aeroplanes correctly, in particular for the rather grim business of bombing targets in Germany, for example. Here's a Lancaster bomber. Here is a thing called the Astrodome. There it is. That's what is underneath it. And they originally tried to navigate bombers by using celestial navigation techniques, but from an aircraft. And the problem with that is aircraft move very, very fast, and it was extremely difficult to get any sort of accurate navigation from them. And it meant that the aircraft were going nowhere near their targets and were basically almost bombing at random. So it was realized during the war that in order to navigate aircraft, you had to use something other than celestial methods, and so electronic methods were developed. And the first ones that were used were developed by the Germans. They used things called beams, and they had, in the 1940s, two types of beam, the Knickerbein beam and the X-Garat. Knickerbein means, I think, literally crooked leg. And the way they navigated was they'd have a transmitter which would send a beam out like this, and then they'd have another transmitter which would transmit cross beams like this. The aircraft would fly along these beams here, and as they passed the cross beams, they would know where they were, and at the final cross beam, they would release their bombs. And a famous target for this was Coventry, and in, I say, 1940, Coventry got very badly bombed because the Germans could navigate accurately. Fortunately for us, a guy called R.V. Jones worked out this system and developed jamming techniques to prevent it. The RAF adopted a rather different approach, which was called the G system, which used what's called the hyperbolic navigational system. And the hyperbolic navigational system relies on finding the difference in the distance from the aircraft to two other points. And what would happen is that you'd have three stations, a master and two slave stations, each of which would send a pulse at exactly the same time. They were synchronized with each other. These pulses would arrive at the aircraft, but at different times because they'd gone different distances. And if, for example, you measure the time of arrival, the time difference between the master station and the first slave, then you multiply by the speed of light, and that tells you how far away you are, the difference in the distance from the master to the slave. Let's draw a picture of that. Here's a master station, there's slave A. If you know the difference in the different distance of your aircraft from the master to the slave, then you lie somewhere on a curve like this, and this curve is the hyperbola, which was invented or discovered by Apollonius about 3,000 years before these navigation systems were used. So you lie on one of these curves, and with the other station measuring the distance, you lie on another set of curves. So if you know you're on this one and you're on this one, by the intersection, you know where you are. And that's the basis of the hyperbolic navigation system, looking at the difference in time and therefore the difference in distance between 2 points. And it's a very good system. It works very well. It had an accuracy of about a mile at distances of about 300 miles, which was a huge improvement on the celestial methods. It's still in use today. There's a thing called the Lunar system, which used it. It was originally developed, in fact, in the First World War to detect where guns were by listening to the difference in times of the sound of the gun from different receiving systems. And I say it was accurate to about 1 mile to 300 miles. And it was the first true electronic navigation system. But now, where we got to in the 21st century, we're not using this anymore. We use GPS. So I thought I'd finish this talk by telling you briefly how GPS works, how errors in GPS arise, and how it all may go terribly wrong in the future. Okay. So how does GPS work? GPS works by having satellites. You have satellites buzzing around the Earth, which are sending signals. And the satellites are so arranged that any person at any point in the Earth will have 5 satellites within sight from where they are. Okay. So that's how they're arranged. So any person will receive 5 signals from 5 satellites at least. So each satellite transmits 2 signals. I'll tell you why presently. And each signal is encoded with the time and position of the satellite when that signal is sent. You then receive those signals at times T1, T2, T3, T4, and T5. So this is when you receive them measured on your receiver. And you have, at the same time, the satellites are at these known positions, X1, X2, X3, X4, and X5. So, this is equal to the true time plus an offset because the satellites are synchronized with each other, but your clock in your mobile phone or whatever may be slightly off. The distance, di, from you to the ith satellite is speed of light c times the time difference between your received time when you're measuring it and the time the satellite transmitted it. Okay, so that's, you know how far you are from each of these 5 satellites. Now, in order to find out where you are on the Earth's surface, you need to know your position, which is 3 coordinates x, y, and z, and also the time offset between your clock and the satellite clock. So that gives us 4 unknowns. So if you measure this for 4 satellites, that allows you to work out your position, x, y, and z, and the time offset. Why do we need a 5th satellite? Well, all of these things have a little bit of an error, and having the 5th measurement allows you to estimate that error and compensate for it. So that's why we use 5 satellites. So essentially 4 to find where you are, and the 5th to correct for errors. And that's how GPS works. Let's talk about errors. When we looked at Harrison with his clock, he had to get a clock accurate to within 4 seconds or less to get an accuracy of 1 mile. If you're measuring everything and then multiplying by the speed of light is so big that even very, very small errors can lead to large distance errors. So a GPS satellite has to be accurate not to 4 seconds a day, but to microseconds per day. So it's really very precise. But still the same point. To find out where you are with GPS, we need to measure time accurately, just a lot more accurately than Harrison did. But Harrison had the right idea. Here's a wonderful error, all due to Einstein. If a satellite's going around the sun, going around the Earth, then it's moving fast. According to Einstein, fast-moving clocks run slow. The satellite is further away from the Earth. It's in a smaller gravitational field. According to Einstein, that means it runs fast. So it's running slower because it's going fast, and running faster because of the gravitational field. These are consequences of relativity theory. If you combine the two together, Einstein's theory of relativity predicts that a clock on a satellite gains 38 microseconds a day. And that corresponds to an error in measurement of 11 kilometers, which is a lot. Your GPS is way, way more accurate than that. And the reason it's more accurate than that is that we compensate for Einstein's special and general theory of relativity. This is the only case I know of technology absolutely requiring Einstein's theory of relativity. But think how great that is. So our sat-navs would not work if it wasn't for Einstein. And I take a great deal of pleasure in that. So I'll whiz on to this to just see how it may all go horribly wrong. Sitting in the audience at the front is one of my students, Tina, and Tina and I work on an area called space weather. And what space weather is looking at what's happening on the sun. This thing here is called a coronal mass ejection, where particles stream out from the sun and come towards the Earth. Why are we interested in this? Because if those particles come to the Earth in large quantities, they can knock out our GPS system. So we are very interested in what the sun is doing because we are so reliant now on GPS and navigation that if we fail to detect these coronal mass ejections or fail to understand and predict when they hit the Earth, all our navigation will get wiped out. And this is an area where mathematics suddenly becomes rather important, to the point that some of my colleagues actually are on the COBRA committee for the government to advise them what to do. And if this does happen, my advice to you is get out your trig tables, get out your ephemeриdes, and start to navigate using the stars. Thank you very much.